Hey, what's up, guys? This is Chung here again. So this time, today's daily challenge problem number 126, word ladder number 2. Right. So this one is very classic one. So basically, this time our task is to transform the word from the beginning word to the end word. Right. And then we can only transform by using this word list, where you know basically only one letter difference can be allowed, right? So for example, from heat, we can transform it into hot, right? Or yeah, I think that's the only thing. Basically, we only allow to change one of the current letter, one letter of the current word to a different letter. Okay, and then so for this one, we want to return all the basically shortest transformation sequences from beginning to end. So this one is not about the length of the transformation, is about all the sequences. Remember, so we need to return all, not only one, right? And we need to print that out. Okay. So yeah, basically, for example, right, we have this. We want to transform heat into cog, right? And this is the word list. So the answer is two. Is like this two paths, because both of these two paths can give us like the shortest step, right, which is 5. Okay, and then the last one, the second one is this one, right? From heat to cog, but we return empty. Obviously, the reason being is that the end word does not exist in the word list. That's why it's empty output. Here are some like basic constraints, right? Um, yeah. So obviously, this one is also like a BFS search, right? And the only difference is that we want to print all the passes, not the not only one of them. So uh, this will make us to make some additional changes, because if you guys remember how the BFS works, right? Basically, every time once we visit a node, right? For example, if we have a node here, right? Okay. Right. So let's say this is the beginning, right? This is the end. So as you guys can see, so for this one we have two paths, right? But if we use the regular BFS approach, where's the every time once we finish visiting the node, right, we mark it to be visited, right? Then by the time the second path reach this node, okay, we see, okay, so this node has already been visited, then I'll not continue, which means we'll lose the second path here, right? So the only difference we want to, well, the only change we need to do here is that we only we should only add all the visited all the nodes to the visited set when the current layer has been processed, which means that so let's say this is the first layer, right? This is the second layer, this is the third layer, right? So when we process this third layer here, so we don't add this node to the visited set until all the current layer have already been all the nodes in the current layer has already been processed, right? So that's the only thing, because let's say there's another layer. Okay, let's say there's another layer like this, 0. But this one, okay. So this is a second layer, right? Let's say even this one, okay, then probably you will see that, okay, okay, so in this case, actually the first layer will be this one, right? And the second layer will be this one, right? So, but here, once we finish processing the second layer, right? Sorry, the third layer, both this one and this one will be added to the visited set. Okay, and by the time we process this layer here, right, we see, okay, so this one has already been visited. So basically this one will not continue, which is correct, right? Because obviously the shortest path is this two path, not this one, because this one has 3, right? So which means that I think our assumption is correct. So and yeah, I think that's it, right? So we only add this because we are getting all the path, right? That's why we should only add this layer, this visited set once after the entire layer has already been processed. Okay. And yeah, so that's one thing. And the second one is that how can we find the neighbors, right? Obviously, because the word can be 1,000, right? So if we try to look for the word the neighbors from this list, right, that'll be at least we need like 1,000 for loop, right? But since all the words are the English letters, right? So and each of the word is like only 5, right? So what we can do is that we can, for each of the word here, right, it's at most 5 characters long. For each one of them, we can just loop through from A to Z, right? And we try to replace each one of them, each one with A to Z, right? This will be what 26 times 5, right? So this one is much smaller than 1,000, right? Than 1,000 times 5, right? So that's a small trick here to improve the performance. And yeah, I think that's it, right? We can start implementing this thing here. We need answer at the beginning. So for the DFS, for the BFS, we need like the Q, right? The DQ, DQUEUE. Okay, and since UEUE, okay, sorry. Since we want to maintain the list, the entire path, right? So instead of a current word, basically I'm just simply maintaining the entire list for the simple simplicity case. Okay, so it's going to be a list, right? And then inside here we have a list of lists, right? Begin word. Basically, each of the element in the queue is a list. Basically, list where contains the path, right? The entire path to the current word. And then we have visited, right, as usual, as a set. And then, okay, then the BFS template, right? For while this one, the BFS template is like this. For this one, in range of length of the queue, right? Let me try to write the BFS template first. So we have a current list. Okay, it's going to be a queue dot pop left. Okay, and then we have a last word, right, in the list of -1, right? And so basically, if the last word is equal to the end word, right, and then we simply answer dot. Okay, we append this one to the answer, right? Otherwise, right, we try to find the next one, right? Look for next layer of words, right? So how do we do it, right? So for I in range of length of the beginning word, okay? Because all the word have the same length, right? Then for C in all the 26 lower English letters, we can do this string dot ask dot lowercase, right? So basically in Python, this thing will give you a string that contains from A to Z. And then the next word is going to be the last word, right? I plus C plus last word I plus 1, right? And then we do two checks. So first, if the next word is in the word list. Okay, so to do that, let's convert this word list to a word set, right? Because set can give us O1 check, O of 1 check instead of O of n in word set, right? And next word not in visited, right? And okay, and then we have a queue dot append the current list, right, plus the next word, right? Because we're maintaining the path. And oh, so here we cannot add visited here, right? Add next word. So this is wrong. We should not add it here because this will block the other path to go through this word, this node, right? So what we said, instead we should have like current layer words, right, equals to set. Instead we should keep this like a set, right, for the current layer, and in the end we update the visited, okay, which means that after this for loop here, visited dot update, right, of current layer of words. Okay, so that's how we update, and then simply return the answer, right? Yeah, so I think let's run it. Oh, okay, accepted, and there you go, right? So it passed, and we didn't break here, right? So we didn't break here, which means that, let's say we have a bunch of like path here, right? It will continue explore the rest node in this graph, right? For example, this is the beginning, this is the end, right? Let's say there's a bunch of other like graphs, nodes later on, right? So basically, we didn't put like a break here, which means that even after finding the path here, it will continue loop traversing the entire graph until all the node has been visited. But I think it's fine because this one, it will improve the performance, but it will not affect the time complexity. Because the worst case scenario is that this one is the last one. Because the worst case scenario, we have to traverse the entire graph regardless, right? So it doesn't really matter if we break or not. Yeah, so I think for the time complexity, we have n words in total, right? So I think for the BFS search, even though we could have multiple path leading to it, but I think it should still be n times, right? Like what? This one, 5, right? This is gonna be 5 times 26, right? Or maybe there's another 5 here, right? 26, and then for another like times 5, right? But this is all like constant thing, right? So I wouldn't worry about this one too much. So in my opinion, yeah, that's basically the time complexity. It's close to the end, basically, right? Yeah, I think that's it, right? So it's just another classic BFS search problem. The only difference is that now this one we have to print out the path, right? And in order for us to print out the shortest path, we cannot add the visited set here, right? We have to add it after the current for loop or the current layer. So that's the only difference. Cool. I'll stop just right here. Okay, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.